Hello everyone. This is lecture number 4 of unit number 2 of our course Heat and Mass Transfer. Today we are going to discuss about the fin effectiveness, and in this lecture we will discuss how to measure the effectiveness of the fin that is utilized to transfer the heat at a higher rate than without fin. So these are our objectives, that we will analyze the finned surfaces, and we will see how effectively the fins enhance the heat transfer. Then we will solve the multi-dimensional practical heat conduction problem using the shape factor method. So these are the objectives of our current lecture, and we will try to solve the problem. We will try to do our studies accordingly. So as you can see, the effectiveness of a fin is given as the heat transfer rate from the fin of the base area AB to the heat transfer rate from the surface of the area AB. Okay, so basically it is nothing but the heat transfer when there is a fin that has been applied, and to the ratio of the heat transfer when there was no fin. Okay, so as you can see here that Q or dot represents the heat transfer in the presence of fin, and this quantity represents the heat transfer when there was no fin that was supposed to be employed. Okay, and as you can see here in this figure, when there was no fin, this is the fin where the fin has to be applied. So from this surface, this much amount of heat that could have been transferred, but when we have applied this fin, since the surface area has increased, so obviously the heat transfer rate will also increase. So for this particular case, as you can see, effectiveness of the fin is given by this formula, and which is equal to efficiency of the fin into heat transfer from the fin upon the area upon the heat transfer without fin. So as you can see here, area of the fin into upon area of the base into efficiency of the fin actually provides the relationship for the effectiveness of a fin. And again, if we further utilize the various relationship that we have earlier derived for the efficiency of the fin and put those values over here, we will get these formulas. Okay, and for you can say for the simple case, the effectiveness of a long fin, in case of a long fin, it is given by Kp upon HAC. Okay, and the thermal conductivity K of the fin should be as high as possible in order to make our fin more effective, because thermal conductivity is associated with conduction. So higher thermal conductivity will offer higher rate of heat transfer from one part of the fin to the other part of the fin. So for example, for fin effectiveness is high for aluminium, copper, or iron, because thermal conductivity of these material is also very high. So the ratio of perimeter to the cross sectional area of the fin, P upon rho C, rho AC, should be high as possible for a highly effective fin. So use of slender pitch, for this reason use of slender pitch is pins is slender pin type of fins is preferred. Similarly, low convection heat transfer coefficient is preferable in order to to obtain a good fin effective fin. So the total rate of heat transfer from a finned surface can be calculated. For example, if we look at this figure over here, this is the total heat rate of heat transfer because of the fin, and from here we can find out that this is the relationship that when unfinned part to the fin part. So this relationship that we have earlier derived, and this is the relationship that we have again earlier derived for the fin, and this will give the total heat transfer rate through the surface which has the fin. Okay, so actually the here the heat transfer from here plus heat transfer from the fin, both will be calculated. As you can see, the area is an unfin area where there is no fin, and the finned area of the fin where it has been applied. Okay, so as you can see, these are the areas, no fin areas, and these are the finned areas, and this is again fin area. Okay, so this is for one fin, this will be the finned area of a fin, because it has two surfaces. Multiplication by 2 means that it has two surfaces from where the heat can be transferred. So these are the various areas that we have discussed right now, which are associated with rectangular surface with three fins. So the rate of heat transfer from a finned surface, as you can see, this is the overall effectiveness of a finned surface, that can be given by this relationship where Q dot represents the total finned. So it actually represents the finned surface as well as non-finned surface as part of the surface. Okay, so this is the total heat transfer when the fin is applied, and this is the heat transfer because of the convection when there is no fin. So the overall fin effectiveness depend upon the fin density, number of fins per unit length, as well as the effectiveness of individual fin. So all these are the factors on which the effectiveness of the fin depends. So the overall effectiveness is a better measure of the performance of the fin surface than the effectiveness of the individual fin. So as you can see, the overall effectiveness is a better measure of performance of a finned surface than effectiveness of the individual fin. Then what should be the proper length of a fin? Okay, the proper length of the fin should be in such a way that it shouldn't be too short or it shouldn't be too long. Okay, so the proper length of the fin, as you can see, is given by this equation, and because of the gradual temperature drop across the fin, the region near the fin tip makes little or no contribution to the heat transfer. So as you can see from in this fin, the fin should be chosen in such a way that when the fin should be chosen in such a way that it is more it provides more effective uh, heat transfer without compromising with the cost. So how to choose the proper length? If let's say that we are taking ml equal to 5, which is generally taken as the value for infinitely long fin. Okay, and if m into l value is equal to 1, that offers a good compromise between heat transfer performance and the fin size. So you can see ml equal to 1. This value represents a better option compared with taking the value the ml equal to 5. As you can see from this table, ml different values of ml, and the effectiveness is given here. Okay, if you notice that after 2.5 till 2.5 ml equal to 2.5, this is how the it has varies, and at ml equal to 1, it reaches to the 0.762 of the fin effectiveness. But after that, if what at 1.5, that it is equal to 0.95, and after that you can see the variation is very less. So in order to choose a proper length, a common approximation that is used in the analysis of the fin is to assume the fin temperature to vary in only in one direction, along the fin length, and the temperature variation along other direction is negligible. And if you notice that this is basically this most of our formulas that we have derived are basically along the one dimension only, and it has a very sound reason why we have derived along only one direction. And this is also most of the fins that we utilized are made from the thin metal sheet, and such as the fins of the car radiator. So we won't be sure for the fins made of thick made of thick material. And studies have shown that the error involved in one-dimensional analysis is negligible, less than about 1% when h delta upon k equal to 0.2, where delta is the characteristic thickness of the fin, which is taken to be the plate thickness of thickness t for rectangular fin and diameter d for cylindrical type of fin. So here this is the concept of heat sink, the specially designed fin surfaces which are commonly used in cooling of electronic component and involve one of a kind complex geometries, and the heat transfer performance of heat sinks is usually expressed in terms of instantaneous resistances, which is given by R. So a small value of small value of thermal resistance indicate small temperature drop across the heat sink and thus a high fin efficiency. So this is the concept of fin efficient heat sink, and the heat transfer is given by utilizing this relationship where Q fin equal to TB minus T of the ambient upon resistance offered by the fin, that is equal to HF of the fin into eta of the fin, that is equal to TB minus T infinity. So heat transfer in common configurations that we have come across so far, we have considered heat transfer in simple geometries such as large plane wall, large cylinders and spheres. This is because heat transfer in such geometries can be approximated as one dimensional only, but many problems encountered in the practice are two or three dimensional and involve rather complicated geometries for which no simple solutions are available. A simple class of heat transfer problem for which simple solutions are obtained encompasses these involving two surfaces maintained at constant temperatures T1 and T2. The steady rate of heat transfer between these two surfaces is expressed as Q equal to Sk T1 minus or T2, where S is the conduction safe factor and K is the thermal conductivity of the medium between the surface. Says surfaces, the conduction safe factor depends on the geometry of system only. Conduction safe factors are applicable only when heat transfer between the two surfaces is by the conduction only. So heat transfer in most common configurations, as we can see, this is how they are given, and different type of shape factors are also mentioned over here. And then some more factors like shape factor for this eccentric circular cylinder of length L in a cylinder of same length is given here, and for the large plane wall it is given over here. A long cylindrical layer is shown over here as equal to this value, and this is again the shape factor that is given over here, and the spherical layer for the spherical layer that is shown over here, and this is for the disc it is again shown over here. Heat transfer and in other configurations, as we can see for other configurations is also shown over here. Edge of the two adjoining wall of equal thickness, then the for this kind of shape is shape factor is this one, and for isothermal sphere the shape factor is this one, and the for isothermal sphere buried in a semi-infinite medium at T2 whose surface is insulated. So heat transfer is given as Q equal to Sk into T1 minus T2. Once the value of shape factor is known for a specific geometry, the total steady heat transfer can be determined from the following equation using the specified two constant temperature of the two surfaces and thermal conductivity of the medium between them. So this is the summary. Today we learned about the effectiveness of a fin, and effectiveness of a fin actually represents the heat transfer rate from the fin to the heat transfer rate when there was no fin on on that particular area. So these are the review questions that you can go through and try to answer those questions, and we will discuss them when need. So these are the references that one can go through and try to study these books. Most of the PPT is made from Yunus Essential and Heat Transfer by Yunus Essential, and this is a very good book. Other books are also very good, and you can refer to any of these for your studies. Thank you for watching this lecture.